Alright, so we have a weird one today. We have the integral from 0 to 20 of the ceiling function of the floor function of x over 2. Now, if you're like me, you looked at this and you had no idea what this notation was. Essentially, it's a ceiling function and a floor function. Now what these do is they're going to round up for ceiling, round down for floor, whatever numbers in them to the nearest whole number, right? So 5.2222 in a ceiling function is going to be 6, and a floor function is going to be 5. That's the gist. And you might be wondering, okay, well, how do we integrate that? Well, you have to think about what integration is, right? It's the area under the curve, right? Integration is finding the area under your curve, right? Floor and ceiling functions are going to look like this. They're going to have these large jumps, right? And if you notice, that kind of looks like, that kind of looks like Riemann sums, right? So, and you can treat them like that because, you're counting from 0 to 20. Anything that's, in between whole numbers is just going to get rounded up to the nearest. So you can kind of, you treat them like a summation, right? So I personally brute force this. Other people brute forced it in a bit more eloquent ways. But yeah, so that's essentially what you're doing. So because they're going to be equidistant because of the rounding nature of it, you can just kind of plug in all the whole numbers, right? So the ceiling function of 0 over 2. The reason for this, like I said, is, if you're at 0.5, you're going to be treated like a 0. So you're going to so from 0 to 1, you're going to be the same number. Which means that you can just treat it as the base is 1 and then the height's whatever the value is. And then, you do the same thing. Well, from 1 to 2, 1 to the limit as it approaches 2, because this is what they look like zoomed up, is going to be 1, and so on and so forth until you get to 20 over 2. You get to 20. Okay, that's the floor function dealt with. So now we have the ceiling function, which once again you round it, and when you do that, when you plug it in, you're gonna find that you get 0 plus 1, 1, 2, 2, plus 9 plus 9 plus 10, and then you add them up. Right? Here's where a bit of like, hey, this is something that'll actually be kind of useful, right? So the numbers from 1 to 9 repeat. So you can rewrite it as 2 times 1 plus 2 plus 3 plus 8 plus 9 plus 10, right? And then here's where we're going to get into some number theory, just a tiny bit. So when you have a sequential sequence like this of natural numbers, you can use n times n plus 1 over 2 to represent it, where n is equal to the last digit of your sequence. In this case, it's 9. So you'll have 2 times 9 plus 1 over 2. Right, the 2's cancel, plus 10. The 2's cancel out, so it's 9 plus 1. So that's 9 times 10 plus 10. 9 times 10 is 90 plus 10. That's a 10 out of 16, I promise. And that's going to equal 100, which is our answer. If any of you have a better way of looking at this that scales better, please feel free to let me know. But this is how I was able to get it done, and how other people I've seen do work through this problem set do it. They did it. They used a bit more of the number theory to explain why. They talked about how you can rewrite the integral as a summation instead, Riemann sums. But yeah,